And we're on. Awesome. All right, let me see if anyone's waiting to join. Nope. Okay, cool. All right, let's get started with review. So I received this practice test paper that the professor gave you. And we're going to use that to do our practice today. Great. There we have it. Okay, there it is. Thank you, Navoni. Practice questions. Awesome. So we'll go over all of these questions, and that will be our first line of review today. And if time permits, we'll go over other stuff. Obviously, if you have any specific questions or specific topics that you want me to go over, feel free to let me know. And of course, if you have a question, just unmute yourself and ask me what you need to. Cool. Before we get started, can you guys tell me if this sounds better or this sounds better? Okay. Both the same. First, okay. So this is not as good as this one. This one's good. Awesome. Cool. Okay. Yep, we're going to go over the practice exam that the professor posted. That is what I have here. Great, let's get started. First question says, let me copy this. 1 second.
You have a towel. There's a shower and then.
Uh-oh, someone's unmuted. Just letting you know. How does this work? So I copy. There it is. Paste. Huh. Does anyone know how to copy and paste in Mac? I know how to do it in Windows, but since this is a new laptop, I have no idea. So I know how to snip it, but how do I paste this? Command B. That's what I'm trying. Maybe Command C, Command B. Okay, there we go. Thank you. All right, here's our problem. Make it a little bigger. Awesome. Density of a 16% mass of a 16 mass percent solution of sulfuric acid in water is something at 25 degrees Celsius. What is the molarity of the solution? Well, this one's easy. I'm just going to write down what molarity is. It's moles divided by volume. Can someone tell me it's going to be moles of what in this particular question? And you can unmute yourself if you want to.
Do you mean the unit?
Moles of sulfuric acid. Good, good. divided by volume of solution. Amazing. All right. Since this is a percentage question, what's the first thing that I do? What's our mantra with percentage question, generally speaking?
Convert it to over 100, so
Yeah.
16 over 100.
16 over 100. So that's like starting with 100 grams of the stuff. So let's start with 100 grams of solution. Because molarity doesn't depend on how much you start with. The molarity of a little part of the solution is the same as the entire solution. Okay, if I take 100 grams of solution, how many grams of sulfuric acid do I have?
16.
16, good, using the percentage. And then I need the moles of sulfuric acid. How do I get that?
Mass by molar mass of it.
Yep. So I take my 16 grams and I divide by its molar mass. Sulfuric acid, if you remember, is H2SO4. I think that has 92 molar mass. You can calculate it. You do that on an exam by looking at the periodic table in your lecture hall or one that will be provided to you and calculating the mass. So yeah, you divide by 92, you get the number of moles. That goes up here. Great. Now, how do I figure out the volume of my solution? $98, yeah, see, it's close enough. Yeah. Thank you. And how do I figure out the volume of my solution? What information am I using here?
The density.
Density, good. Density, which is mass over volume. So I'm gonna solve this for volume, which will give me mass over density. Awesome. What mass goes up here? Is it going to be 16? Is it going to be 100 minus 16? Or is it going to be 100?
I have a question.
Mhm.
So on the right side, you wrote 16 grams over 92 grams.
Grams per mole.
Is it 92 or 98?
Oh, it should be 98. I see. I see where I messed up. Okay. Thank you. Yeah, 98 grams per mole. Great. And so volume is mass over density. Tell me what mass goes up top. I know the density. I can look at it. It's 1.1094 grams per milliliter. What goes up top? So you have three kinds of masses here. You have 16 grams. You have 100 minus 16 grams, which is the rest of it. And you have 100 grams. What mass do I use?
Hundred.
100. Good, because this whole equation is being applied to solution, not to water separately, not to sulfuric acid separately, but to the solution as a whole. So we're interested in the volume of the solution. This is volume of the solution that will be equal to the mass of the solution, which is 100, not water, but the whole solution, divided by density of the whole solution, which is 1.1094. So good. You would use the mass of the whole thing. This, let's say, is some number star that goes down there. Well, that's not exactly true, right? when you divide these two numbers, what's the answer going to be in units of? What's the unit here?
It's going to be milliliters, so convert it to liters.
Awesome. Milliliters, because the density was in units of grams per milliliters. Yep. Convert that into liters. Let's say you get star prime. That goes here. Good. Divide by 1,000. Great. Easy. This is as difficult as concentration questions get, pretty much. All right, moving on. Maybe I can just do this. Yep, much better. So solution of molecular non-dissociating compound, okay, was prepared by adding blah, 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 blah. The boiling point of the solution was raised. Interesting. So this seems like a boiling point raising question. That reminds me of colligative properties. Okay. What equation do I use here? This is the second chapter, right?
It would be the change in TBI and then KBM.
Good. KB times M. Awesome. And like we said, delta is always going to be solution minus pure. So it's going to be, whoops. Let's just expand this real quick. TB, which is of the solution, minus T0B, which is of the pure solvent, equals I times KB times M. Awesome. Let's start plugging in things. What's TB here?
Zero 0.520.
0.520. Okay, what would T naught B be? So if you say that this is 0.520, what is this?
Zero, because it's saying it was raised by 0.52 degrees Celsius.
So the 0.52 degrees Celsius here is neither this nor this. It's this. It's the change. They've given as the value of the subtraction itself. So you would use the first one, 0.520 degrees Celsius equals I times KB times M. What's I here?
1.
Good. And the reason?
It's molecular.
Molecular. Good. They have really gone out of their way to tell you that I is 1. It's molecular and non-dissociating. Okay, KB is given directly. That's 5.02 degrees Celsius per molal, MOLAL, times molality. Do we have molality given to us explicitly? Nope. So I'm just gonna put a fraction so we can input in data for the molality. Okay. Remember, molality is moles per kilograms of solvent. Thank you. What goes on the bottom here? (0.05). Good, because our solvent is carbon tetrachloride Its mass is 50 grams, but we want to convert this into kilograms, which gives you 0.05 kilograms. Awesome. And what goes on top? Moles. Do we have moles explicitly in the question? No. So I'm going to expand moles again. Anytime I don't have something explicitly, I'm just going to expand it into what it is. Moles is given mass over molar mass. Given mass here is okay, so where does 0.35 go? Up or down into this fraction? Is 0.35 the numerator or the denominator?
The numerator.
Numerator, good. And what goes in the denominator? Don't know. Let's just call it X or molar mass mm. Great. Solve for mm and you're done. We did an exact question in class, I believe. Good. Very good. Any questions? Awesome. Moving on.
We did this one in class.
Mhm. Say that again.
We did number 3 in class.
Oh, you did number 3 in class.
Yeah,
Awesome.
professor.
Is this a good one or a bad one? Let me check. Oh, this is the weird one. Oh, okay, great. If you did this in class, that's great. I've also, yeah, also I think I recorded a little video explaining this. It should be in your email. Cool. We're gonna skip 3 because I went over this. Awesome. 4. For the following reaction, A plus B gives C, blah, blah, blah. Okay. Okay. For the following reaction, A plus B gives C. If the reaction is first order with respect to A, what is the concentration of A after 12.2 minutes if the initial concentration was 3.02 molar? Okay, this is first order kinetics. What's the first order equation? It's concentration of A equals concentration of A at time equals 0 times e to the minus kt. And also, since this is first order, we have a separate equation for half-life, which is that half-life equals ln2 over k. Awesome. We're trying to find the concentration of A at some time, so that's what we're trying to look for. A naught is given 3.02. E to the minus time is given 12.2. You can have time in whatever unit you want. Just make sure that the half-life is also in that unit. So minutes and minutes, that's good. I don't know what K is. K is not given. How do I figure out K? How do you figure out K?
Plug in 5.71 for T of 1/2.
Awesome. We know half-life, 5.71 equals ln2 divided by k. Yep, solve for k, ln2 divided by 5.71, which is some number. And that number goes up there and you're done. Great. Easy enough. Let's look at the next one. There's 5. Okay. Benzaldehyde has a normal boiling point of blah, 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 and a critical point at 422 degrees Celsius and 45.9 atm. Calculate the vapor pressure at 145 degrees Celsius.
Can you just go up real quick so I can just see the solution again?
Sure.
All right, thank you.
Great. What do we have for vapor pressure? I believe I did not go over the equation in class, but you should have seen it in lecture. Vapor pressure has this equation. Yeah, the Clapeyron equation, CC. Which goes ln P1 over P2 equals delta H vapor pressure divided by R times 1 over T2 minus 1 over T1. Yeah, Navodi?
So if we start with T2 minus T1, is it always negative in like any equation? Like the change in H of vaporization?
Yes. I think, yeah. You always need to give the substance heat to make it evaporate. Yeah.
And that's like, that applies to any equation with the change of temperature, right?
Wait, now I don't think I understand your question.
Sorry, okay. So you know how like in this equation, you could do ln of P2 over P1.
Yeah.
So if you do it that way, is it a negative constant?
If you do T1 minus T2,
Actually, never mind. I don't think, because I thought this equation was P2 over P1.
oh
Neg-
yes, it is. I'm sorry.
Okay.
You're right. It is. It is P2 over P1. Yeah, the P's and the T's should have opposite order. If it's 2 and 1, then this would be 1 and 2. T1 and T2. So whatever order you choose them, it doesn't matter, but make sure that the P's have opposite order to the T's in this particular equation. Was that your question?
I thought it's negative. Maybe I just need to look over the equation. It's okay. Thank you.
There's variations. If you do ln, if you keep them in the same order, so ln P1 over P2 is the negative of P2 over P1. So going from here to here requires me to put an additional negative. that I can transfer to the other side. And that's how I get the, yeah, you might have seen it with the negative in there. So if you keep the order the same, then you need to introduce a negative. Okay, cool. All right. You use whichever equation that you have on paper, it's the same result. Okay, cool. We have here, what do we have? We have that the normal,
So I was just looking at the old notes from the lecture, and the professor writes it in a bit different way, even though like he doesn't switch the ln p2 over p1. He switches 1 over t2 minus 1 over t1, and he makes it a negative in front of the change in
Yep.
enthalpy.
Yep.
We can do
So
that
this
too.
is like a minus b, which you can also write as b minus a at the cost of taking out a negative.
Okay, that's the one. That's how he writes it. Then he
Yeah,
says,
there's many ways you can write this equation.
okay.
Yeah, depending on how you take out the negative. It's all the same. Yeah. Okay, cool. So what do we have? We want to calculate the vapor pressure at 145 degrees Celsius. So let's call that temperature 1, 145 degrees Celsius. P1 is unknown. At a different temperature, 179 degrees Celsius, this is the boiling point. What is the vapor pressure at boiling point of anything?
1 ATM.
1 ATM, right? Exactly. So that's 1. That's something we keep in mind. The normal vapor pressure, the vapor pressure at the normal boiling point is always 1 atm. Great. So we have P1, we have P2. Just need to figure out what this annoying delta H vaporization is. Oh, never mind. We're actually given more information here. We also have another temperature given to us. Let's call it T3, which is 422 degrees Celsius. And the pressure at this temperature is the pressure here is 45.9 atm. So why do you think we were given 3 data points? What's one information in all of this that's missing? We have various pressures, we have various temperatures. R is a constant. Whose value do we not know to begin with?
Delta H of vaporization.
Yes. So that's why you have these 3 values. You're going to use 2 sets of full values to figure out delta H vaporization, and then you're going to use that equation to figure out the other thing. You can also do it like this, which I think is even better. Will save you some trouble. Let's do it like this. Let's write down an equation. So the first method is to just go ahead, plug these 2 values, these 4 values in, and calculate your delta H vaporization. And when you have that, then use this data set with any of the other 2, and you figure out your P1 that way. That's the easy way, or the straightforward way. Another way, which will save you some time, is to write down the 2 equations, but divide them out. The unit of pressure doesn't matter here because it's a division of pressures. Yeah, as long as the units match, you're fine. Yeah. Temperature here, the units do matter. They have to be in Kelvin. Okay, so ratio ratio makes pressure mean ratio. If you have a ratio of pressures, then pressures can have any unit. If it's a difference, then temperature can have any unit except Fahrenheit. So it can have Kelvin or Celsius. But if you have 1 over stuff, then you got to use standard units. So here you want to use, you want to convert these temperatures into Kelvin temperatures first, which is what we'll do. Great. But here's what I want to do. I'm gonna just directly, actually, let me just calculate these temperatures in Kelvin real quick, because that's an annoying second step. Okay, what do we have? 145 plus, I'm just gonna do 273 and ignore the 0.15. 179 plus 273, 452. And lastly, 422 plus 273 is 695. Great. So from the first two, I get ln, P2 is 1, P1 is just P1, equals delta H vaporization over R, 1 over T1, that's 1 over 145, minus 1 over T2, oh no, 1 over 418 Kelvin, right? 418 minus 1 over 452. Take that as your first equation. And then from the second two equations, I'm going to have ln, what is it? Doesn't matter. P2 over P3, so that's 1 over 45.9. So I did 2 over 3. So in the temperatures, I should reverse it. Equals delta H vaporization over R. Temperature 3 is 1 over 695. Temperature 2 is 452. Take that as your equation 2. And since we don't want to go through the trouble of figuring out delta H vaporization in this method, just divide the two things. Hour and a half. All of that goes away. And that's the use of dividing these two equations. ln of 1 over something is negative ln of that thing. This here is some number. Put that in a calculator. Let's call that number 1. Put this in a giant thing in a calculator. That's another number. And this whole mess in a calculator, and that's your third number. And now solve for P1. So ln of P1 would be number 1 times number 2, negative, divided by number 3. E both sides, and you have your P. P is going to be exponential, so E of negative of the first number times the second number divided by the third number. So if you do it like this, if you divide equations, then you can skip the step where you solve for enthalpy of vaporization, delta H vape, explicitly. That can save you some time. Any questions?
Sorry, but can you walk me through the problem again, logic-wise?
Sure. You have the CC equation, and you're given two sets of temperatures and pressures, and one where the temperature is given, but the pressure is unknown, right? For a general Clapeyron equation, you just need two pressures and two temperatures. Here, you're given three temperatures and two pressures. That's weird. And we realized that that was the case because you needed extra data to figure out your delta H vaporization, which is not given in the question, right? So what you could do is you could take these two pressures and temperatures and use that to figure out your delta H vaporization. That would be one way. And then come back to solve for P1. Do you understand that part?
Yeah, I understand how to do that.
Yeah. But I'm saying that takes longer than if you just write two equations and you divide them instead. So what I did here is I made a system of equations. I made the first one by considering these two pressures and temperatures, and the second one by considering these two temperatures and pressures. For the red one, P1, P2, T1, T2 are already marked, so you can input it as is. For the second one, you have T2, T3, P2, P3. Well, rewrite the Clausius-Clapeyron equation in terms of 2 and 3. That'll be ln, I'm going to replace 2 with 3 and 1 with 2. So it will tell you where to put numbers now. 1 becomes 2, 2 becomes 3. And now input in your values. That gives you your second equation. Divide and smooth sailing from there.
Thank you.
Got it? Yes, can do. Oh, okay, 1 second. Awesome. So the units of pressure that you need to know are ATM, millimeters of mercury, pascals, and perhaps bar. 1 ATM is 760 millimeters of mercury. 1 bar is just 10 to the 5 pascals. 1 ATM is 1 point, what is it? I forget. One point 0.01325 times 10 to the 5 pascals. But we know 10 to the 5 pascals is a bar. So 1 ATM is also 1.01325 bars.
What about torr? Some problems had torr in them in Alex.
Yes, torr is very simple. Torr is torr and mmHg are the same thing. Torr is just another name for millimeters of mercury. Okay. Awesome. Moving along. Oops. 6. Okay. It's the vapor pressure of a solution at 20 degrees of a saturated solution of the non-volatile solute, blah, blah, blah. Vapor pressure is the solubility of 17 grams of urea Oh, the solubility is 17 grams of urea in 100 milliliters of methanol. Density of methanol is given, and the vapor pressure at 20 is 95.7. Okay. Yes. So this is a solution question, right? Remember, for a solution question, you always want to come back to the last 4 equations in chapter 2, colligated properties questions. So we had, first thing we break this down like this, right? The pressure of a solution, that's what the question is asking us about, pressure of a solution, is made of the pressures of its components. So we have here pressure of urea plus the pressure of methanol. Urea is explicitly stated to be a non-volatile solute. So what is the pressure of urea? What's the pressure contribution of urea if it's non-volatile?
0.
0. Poof, goes away. So all we need to do is to figure out the pressure of methanol in solution. And that, we recall, is given by I times P0 times mole fraction of methanol. So this is also of methanol. Methanol, no information is given about whether it's molecular or ionic. What's your guess? What is the I value for methanol? Yep, it is an organic compound, so it's molecular, and so the value is 1. P naught is the pressure of methanol just on its own. 95.7. This is pure methanol. Times, we just need to figure out the mole fraction of methanol, which you know how to do. Moles of methanol divided by moles of everything. Okay. How much methanol, how many grams of methanol and how many grams of urea do we have here? I don't know. It says that you have 17 grams of urea in 100 milliliters of methanol. Okay, so let's say urea is 17 grams. Methanol is 100 milliliters. How do I figure out the mass of methanol? What information do I use?
The density of methanol.
Good. Density is mass over volume. And so mass is density times volume. So it's that 0.792 times volume is 100. And that tells you something in grams. Great, you have both grams. And now you want to convert them into their respective moles. So you can do the mole fraction thing. Divide 17 by the mass of urea, which I don't know what it is, but there you have the chemical formula, something. Same thing down here. Whatever grams you get, divide that by the molar mass of methanol. I'm surprised that they haven't given you the chemical formula of methanol here, but in case you don't know, this is it, CH3OH. Don't think you should memorize that. Which is why I'm surprised they haven't given you the chemical formula here, but whatever. So that molar mass goes down here, and then you know how to take the mole fraction of methanol. Moles of methanol divided by total moles. Got it? Any questions? Oh, wow. You need to know the chemical formula of methanol, really? Okay. 1 sig fig or 2? Great question. Let's analyze our sig fig stuff here. This has 3 sig figs. Your molar mass will have a bunch of decimal places. So the limiting, the smaller one would be 17, which is 2. Same thing here, I guess. No, here you have more because this is 3 and it's 100.0. That's 4. So the minimum there is 3. But then when you figure out the total, the methanol goes, the methanol goes up here, which is 3. Stuff goes down here, but it involves a 2. Yep, 2 is the smallest amount, is the smallest sig fig. So you're trying to minimize, because this is all multiplication, the number of sig figs, so that would be 2. Yep. Round your final answer to 2 sig figs. Yeah. Or actually, I don't know, because when you calculate total moles, you're adding 2 things. And the rules for addition are different. You're minimizing number of decimal places. I have a feeling if you do that, you'll still end up with 3 sig figs. Try. So do this, divide by molar mass, divided by molar mass. And once you do that, when you add them up, see how many decimal places you have. If you follow the rule of minimizing decimal places, I feel like you'll still get 3 sig figs. And so I think your answer should have 3 sig figs all the way at the end. Make sense to everybody? All right, cool. Yeah, 3, right? Yeah. So the final answer should have 3 sig figs. Awesome. Moving along. Is that it? No. 7. How many questions do you have in total? Okay. What's the activation energy for the first order decomposition of blah, blah, blah? You only have one equation that deals with activation energy. It's the Arrhenius equation. Give me 1 second. What is the Arrhenius equation again? Let me look that up. Arrhenius equation is ln there. ln. Yep, that's the one. That's Arrhenius equation. K1 over K2 equals over R you might have a negative. I'm just going to flip the order instead. Minus T2. And we are trying to get, did I copy the wrong question? Yes, I did. C, C. Okay. What do we have? Rate constant at 32 degrees Celsius. Temperatures are in inverse form, so we have to use exact Kelvin temperatures. 273 plus 32. This is, I'm just saying, this is basically plug and chug, right? That's your T1 when you convert it properly. This is T2 when you convert it properly. This is K1 directly given to you. This is 10 to the negative 5. And 10 to the negative 5, this is K2. Plug everything in. Your R, because this is activation energy question, it's going to be 8.314. And solve for EA. Joules. Any kind of energy has units of joules. All energy has units of joules. Okay. Right, I'm not even going to do it. It's literally a plug and chug question. Unless someone is confused. All good?
For the last one, for the last question, number 6, how did you find out total moles?
Add. So figure out your number of moles of urea. You have 17 grams, divide by molar mass. That's moles of urea. Methanol, do the same thing. Then add them up.
Oh, they're separate. Okay, I thought it was together. Okay.
Nope, two different things, yeah. Great. Moving along to question 8. Okay. Molarity is given, density is given, mass percentage is what you need. Okay, so molarity is 5.23. Density is 1.20144 grams per milliliter. We need to figure out the mass percentage of the solute. Yep. What is the, yeah, understandably. Anytime they say it's an aqueous solution, you know the solvent is water. That's what aqueous solutions are. And then the other thing is your solute. Mass percent of the solutes, the mass of barium chloride divided by total mass, which is barium chloride plus water times 100. Amazing. So we need these two masses here. Great. So what do we do? We somehow need to combine these two pieces of information. What does 5.23 molarity mean? It tells you how much BaCl2 there is per liter of the solution. right? You have 5.23 moles of barium chloride per 1 liter or 1,000 milliliters of the solution. Great, but we care about masses. We don't care about milliliters. And so let's convert the 1,000 milliliters of the solution to grams. Density equals mass over volume, and so mass equals density times volume. That would be 1.20. Well, multiply that by 1,000, move the decimal over 3 times. 120.144. No, 3 times over. So that's 1,201.44 grams of solution. Awesome. So we have the volume, we have the grams of the solution. Where does this go? Here or here? Up or down?
Down.
Total mass is mass of the solution. Awesome. And how do we figure out the mass of BaCl2?
From the mole formula.
Yep. We know how many moles there are. Multiply that by the molar mass of barium chloride. You get the grams of barium chloride. Let's call that some number, and that goes up here. Times 100, and you're done. How do I find the mass of water in this case?
Total mass minus the barium chloride mass.
Exactly. So now you can imagine a variation on this question, which is they give you molarity, they give you density, and then they ask you to calculate molality. Okay. Molality is moles divided by kilograms of solvent. You have your moles, 5.23, but then you take the 1,000 milliliters of the solution, you convert it into grams of the solution, you take your 5.23, you convert it into grams of solute and subtract, and that goes into the denominator for molality. 5.23 divided by the subtraction. Okay, so that's a variation on this one. Any questions? Okay. Awesome. Question 9. Oh, this is it. 8 questions, huh? Okay. Do you guys have any other questions? Any other practice thing that you want me to go over? Or any topic that you want me to make up a question on?
So for the total mass, at the bottom we're subtracting the total mass minus what exactly?
Your thing has 2 things, right? You have water and you have BaCl2. If you want to figure out, your solvent is water. If you want to figure out the mass of the water, well, you subtract the other thing from the total.
Are
BaCl2.
we trying to like find the total mass though? I thought we
Oh, no. I was talking about the variation on question where suppose the question told you to calculate the molality instead. Okay, not for the present question, not for this question as it is. Yes, there the total mass is 1201.44, which this is. Okay. But suppose instead of asking you for mass percentage, the question asked for molality. The denominator of molality has kilograms of solvent. To do that, you would need to subtract.
Oh, okay. So you're just talking about like if it asks for molality, then
Yes.
okay.
Yeah.
But for this question, we just need the 1.1204 and minus or the grams of BaCl over the total mass, and that's it.
Yeah, true. That's it. That's the one. All right. Any other questions? You can tell me a topic to go over, anything like that.
Can you briefly go over the potential energy, like the graphs?
Yeah.
Endo and exo.
Yeah. The activation energy ones.
Yeah.
Cool. Very simple. Energy. There exist two types of chemical reactions in the world, endothermic and exothermic. Let's plot both of them. If you start from a higher energy level and then you end up at a lower energy level, well, then that missing energy was released, and that's an example of exothermic. If you start with some energy, but then you end up with higher energy at the end, then that additional energy was sucked in from the surroundings, and that's an endothermic reaction. So the first thing is reactant in both cases, and the second energy state is the energy of the product in both cases. To go from the reaction to the product, every reaction in the world requires a little energy hump. So you can't just neatly slide down. You have to make so the reactants, for them to combine to form products, they have to first form this unstable intermediate, which has a higher energy than both the reactant and the product. So in both cases, you have the graph that looks like this. And then if you put a catalyst in, then that hump drops down, it becomes lower. I'm going to draw that in green. The energy difference between the initial and the final, I'll do this in a different color, is called the enthalpy of the reaction. Instead of drawing an arrow like this, in each case, let's go from initial to final. Initial to final. Since this is going down, the enthalpy of the reaction, delta H reaction, is going to be negative. Since the energy of the system is going up in an endothermic reaction, let me mark this. This is exo, this is endo. The delta H, since we're going up, is going to be positive. But the value is the difference in height. And then lastly, what you need is the height of the energy hump. If it's the uncatalyzed reaction, it's that height, EA. And if it's a catalyzed reaction, then it's that height, EA. Same thing for the other cases. Got it? I think I covered everything here with this, unless I'm missing something.
So are these like the main topics that we really need to know for these 3 chapters? That's just these like 8 questions and stuff like that?
Pretty much. Let me see if anything is missing. Go over solubility from chapter 1. You know those well questions? You might have seen them in Alex, where precipitate forms or not when you change the conditions. Yeah, so there's the, in the second chapter, you have the 4 equations at the end. Those are important. But the kind of questions that you will see in this section, you've already seen in the 8 questions that we've covered, specifically as it relates to boiling point and vapor pressure. Melting point is the same. Remember the negative sign. Osmotic pressure is very similar. And then in the second chapter, you also want the CC equation, Clapeyron. How does the vapor pressure changes with temperature? Any question that has to do with the solution, you come here, this box. Anything that has to do with pressure versus temperature, CC. Maybe Henry's law for gases, right? More pressure, more dissolved gas. You could be asked to calculate Henry's law constant, or given a pressure and asked to calculate the solubility, or the other way around. Mass percent, molality, that's all easy. You don't have to worry about that. You already know that. So that's basically chapter 2. Didn't really see questions from chapter 1. Remember the last topic, lattice stuff? Oh yeah, heat stuff, right? You have 2 equations. The state change, which is N times delta H, and the temperature change, which is M times C times delta T. Review our notes where we had, I give you a long question where you have to first heat up the solid, melt it, heat up the liquid, evaporate it, and then heat up the steam to get from initial to final. And then you add up all those little heats along the way. And in the end of the chapter, we had the lattice stuff. What you need to know here is, yeah, that's why I didn't see lattice questions, which I found interesting. Lattice, where you want to memorize the relationships between the cell, the edge length, and related to the radius. Those 3 equations. You can expect questions like, okay, let's do this real quick. You have simple cubic, you have face-centered cubic, and you have body-centered cubic. Face-centered cubic, you just have 8 atoms at the corners, at the 8 corners. in face-centered cubic, you have the 8 corners in addition to each of the 6 faces. So that's 1, 2, 3, 4, 5, 6, 8. And then you also have 1, 2, 3, 4, 5, 6. And then lastly, in BCC, you have the same stuff as before. Eight corners in addition to a body center. So 1 in the smack center. And then remember, corners are an eighth. Only an eighth of each atom in the corner is inside the unit cell. Face, only half of it is inside the unit cell, and body, all of it is inside the unit cell. And so you may get questions like, how many atoms are there inside a unit cell of FCC? How do we do that? There's 8 corners with 1/8 contributions, and there's 6 faces with 1/2 contributions. That's 4. What about BCC? 8 times 1/8 plus 1 times 1, 1 in the middle. That's 2. Here, 8 times 1/8, and that's it, 1. How do we calculate the, what's the relationship between the radius and A, the side length? This is A in each case. Well, let's think about it. In simple cubic, the corner atoms are touching each other. So the edge length is from the center of one atom to the center of the other atom. So that's like half of the radius going this way from one atom, half of the radius going the other way. So that's 2 radii, A equals 2R. In FCC, atoms touch along the face diagonal. Face diagonal, that's a 2-dimension, right? That's A square root of 2. And you have an atom touching an atom touching an atom. So let's see how many radii it takes to go from there to there. 1, 2, 3, 4. That's the relationship between there. And in BCC, atoms touch along the body diagonal. Body diagonal is 3D thing. So that's A square root of 3. Once again, 3 atoms are touching each other, so it's the same story as here, 4R. That's how you figure out these relationships. And then in each case, you may have questions that say, what's the volume of each cell? The volume of each cell, it's a cube, right? It's A cubed. Maybe they'll give you your radius, so you'll use the appropriate equations, this one, or this one, to figure out A, given the radius, and then cube it to figure out the volume. They could also ask you the mass contained within each unit cell. I think someone brought up an old test paper that had this question, this exact one, where what's the mass of a unit cell in grams or something? Well, how many atoms are inside a unit cell in SC? 1. So it's going to be 1 times, look up the molar mass of whatever atom is making up this lattice. But the molar mass is the mass for 1 mole of atoms. You're only looking for the mass of 1 atom. So you want to divide this by Avogadro's number, because you're only looking for the mass of 1 atom. That gives you the mass, the tiny mass contained within a unit cell. Same thing here. Here we have 4 atoms effectively inside the unit cell. So 4 times molar mass divided by Avogadro's number. So you get the mass of 1 atom, or 4 single atoms. Here, it's going to be 2 times. These are the numbers I'm looking at. 1 times, 4 times, 2 times. Divided by Avogadro's constant. And then lastly, you can be asked, what's the density of each unit cell? Well, mass divided by volume. Mass is 1 times this divided by that. I just copied this. Volume is A cubed. And repetition. A cubed. This was it. This is what it was. And I think that's all you need to know from the lattice stuff all the way at the end. You may have conceptual questions from identifying hydrogen bonding. Everything has, it's all nested boxes, right? Everything has dispersion. Only some things have dipole-dipole. And of the things that have dipole-dipole, some have hydrogen bonding. Covered that extensively in class. You might need to use that to arrange compounds according to their boiling points, their melting points. So the idea is very simple. Strong intermolecular forces. The stronger the intermolecular forces, higher the boiling point, higher the melting point, lower the vapor pressure, and so on. Yeah, that's it from chapter 1. We've done chapter 2 extensively, and chapter 3 was last time. You have that fresh in your memory. Yeah, that's all I can think of. Anything else? All right, then. If there's nothing else, good luck on the exam, and I'll see you guys on Thursday. Yep, no problem.
Thank you.
Yep, all good.